So what happens when you're defining your work in physics and it turns out that your force and your displacement are not exactly in the same direction, which definitely can happen. So what do I mean by that? Well, if you are moving along and you have your displacement, say right there, so how you label your displacement doesn't matter. So if it's this, okay, if you're using an S or if you're using an X, okay, all of these work for us. Maybe I'll just stick to one of them. So if you have this displacement, let's say it's to the right as it is, we know that if our actual force is in exactly the same direction, right there, so let's say if this was our force vector, then all we needed to do is, in order to define our work, it was just simply the magnitude, which I'll write without the symbol for the vector. So magnitude of the force times the actual displacement. And that was our work, right? So that's the definition of mechanical work. Now, I can put up a link up above there where I go into a little bit more detail. Now, for this is all nice and great, and those are the instances where this becomes very simple. But as you can imagine, I can certainly take this vector, I'm going to shift it out here, and then I can shift this vector. But, what happens if it's not exactly in the same? So if I align these two vectors side by side like this, what if my force vector now, all of a sudden, is at an angle? Okay, as it is. So now what angle this is, I don't know. I just shifted it. So here, let me take a protractor. So it looks like, okay, about 40 degrees, okay, right there. So let's just assume that it's at 40 degrees. All right, so if I have that, well, then what happens to this? Well, so in this instance, we can't just blindly take the magnitude of my force vector and then the magnitude of my displacement vector and then multiply them together. So what turns out to be the case whenever you do want to be able to define work, so if you have this particular work, then what you will take is, you're always going to take the force vector, but you're going to take the component of the force vector that is really projected down onto, okay, your displacement vector. And this will bring you back to trigonometry, or basically just the kind of reminder of cos. So now, how would we break down this vector? So if you take a look at this, and I take this force vector as I have it, so let me take this, I'll duplicate it, bring it on the side over here. I can certainly break this force vector into its components, right? So I can break it into its component where I have just its x component, okay? And then I can also break it down so that it is, okay, in its y component. Now, so I can break it into these two components. Now, it turns out that this particular component, okay, as you can see there, so if I take this component, okay, and I project it down onto here, so that looks like that's the component that is actually in the same direction as my displacement, right? So that's what I would have. So then I can go back and say, okay, well, we're going to now redefine work. And in general terms, so instead of just assuming that force is always in the direction, which most of the time it will not be, what you're going to do is you're going to now define your actual work by taking the force vector, so the actual magnitude of it, and you're going to project it down onto your displacement. Or in other words, you need this angle right there, so the 40, and that angle is going to be cos, okay? In this case, it's 40, but in general, for whatever angle it is, it's cos theta. And then you're going to multiply it times your displacement magnitude. Now, very often when you write this out, you might just simply write it out as F multiplied by the displacement. These are just magnitudes. And then whatever the angle in between them is, you're going to take the cos of that. And what that does is, no matter, right, how your actual two vectors are, so it doesn't really matter, how they're positioned. So in this case, they're positioned this way, but you certainly could have had them in any way. So it could have been like this, could have been like this. And all you really care about is what is the angle in between them. and you want to know what their magnitudes are. So once you know what their magnitudes are, and you know what the angle in between is, you can calculate what work is. Now, this brings us to really kind of an important concept because of the fact that if you notice that the angle between them, if the angle is 0, which means really they're in the same direction, so if the angle is 0 degrees, you may recall that cos of 0 is just simply equal to 1. And of course, if it's equal to 1, then indeed this is the definition, okay, of work, which is the original definition of work that maybe you have run into in your kind of introductory physics. But for most of the cases, unfortunately, it may not be always in the same direction. And that shouldn't really throw you off in any way, as long as you're kind of comfortable, or at least your teachers have exposed you to finding out what the cos of an angle is between two vectors. So here I want to give you a few examples of this just so that you don't feel like this is something way beyond your head. So just in summary, so if you were writing this out for yourself, then work is nothing else but simply equal to the magnitude of the force, which you can certainly label it like this, which is the two lines which just basically are taking the magnitude. It is multiplied by the magnitude of the displacement, and however you write your displacement, if it's kind of with a D or with an S or with an X. And then you're going to have to take into consideration whatever angle it is, and you're going to have to take the cos of that angle. The actual units, they're still the same. So they're still Newton meters or simply joules. So that's what you will have and run into. So that's not a big deal there. And very often in textbooks, instead of writing it in the magnitude form, which also, throws students off, this will just simply be written in this way, where work is equal to the force, which is the magnitude of the force, multiplied by the magnitude of the displacement, and then times the cos of whatever angle in between that we have. So let's take a look at some quick examples here that I've kind of posted up. So here's one of the examples, which has actually 40 degrees, which is the one that I drew out there. But it now gives us, the magnitudes. Notice that the directions are there. Not that we care much about the directions, but if we wanted to find out what the work is, so here what we would do is we're going to take, all right, what's the magnitude? Just make sure that it is in SI units, so meaning that it is in newtons, right? So that's 37 newtons. Okay, maybe I'll write that down. Then you're going to be multiplying it. So again, so this, make sure that it's in SI units. So it must be in meters, your displacement. If it's in centimeters, right? If it's in inches or something like that, then you have to change it back to meters if you want joules, okay, as your answer. So this would have been times 56, okay? So times 56 meters. And then, moreover, now you're going to have to take this and you're going to need the angle in between. So you check the angle and then you're going to take cos of the angle. So in this case, it's 40 degrees. And now you can pop out your calculator and you can go ahead and do that. So 37 multiplied by 56 and then multiplied, look for your cos button. And then you're going to take it of the angle that you have. Make sure that it's in degrees. And you can hit your equal sign, and then that will give you an answer. So I'm going to just round this. Notice this is 2 sig figs, so I'll round it. So 1587, this would be Newton meters or joules, or if you're rounding it to 2 sig figs, this would be 1600 joules. Okay, so that's how you would actually do this. Now, it doesn't matter what the angle is, right? So it does not matter. But there are some special angles that you will have that you can find this out. So when you're doing this, so for instance, here's a special angle where you have your actual force, okay? And we're assuming that these are constant forces that are applied. So now you have 4 newtons. Notice that it's pretty much straight upwards, okay? And then you have your displacement. Notice in this case, I put the displacement right here, okay? And I put an S just to kind of throw in that yes, indeed, you can use S, okay, depending on who's teaching it. So here, that's my displacement, so it's 14 centimeters. Now, I might be tempted and start saying, 14 centimeters, I got to change this to meters. This one is in newtons, I can multiply them. But notice that this is 90 degrees. And there's one important feature that you should know or you should remember, that cos of 90 degrees, so if the angle in between your force vector and your displacement vector is 90 degrees, they're perpendicular to each other. And in that case, this actually is equal to 0. And you should know this, that this should make sense to you, that it will be 0. Because if you're going to take this vector and you're going to try to project it down, so if you take this vector and you try to project it down into this, well, it's going to project down basically into a dot. There's nothing that it can project. There's no component of it that will go down in the same direction as your displacement. So what this tells us is that if you're exerting a force, and it's a constant force, and it's perpendicular to the displacement that you have, then your work, no matter, you can certainly calculate your work. You can say force, you can multiply it by the displacement in here, and then you can take the cos. But in this case, whenever this is going to be 90, well, this right away is 0, which means that the work, okay, is 0. Now, this is the mechanical work, okay? So that's the energy that's actually transferred into that particular object. Well, there will be none in this case. So don't get caught with that. So please do remember, okay, that for yourself. Now, another very interesting angle is, now you might say, well, this may not really happen, where your force that you are working with, so notice your force, okay, is in this direction, but your displacement is in this direction. And now you might say, how in the world are you going to do that, right? How can you have a force which is in the opposite direction, okay, as the displacement? Well, don't forget, okay, that can happen. So if you have force of friction, right, and then the object is actually moving, so if you have an object, okay, and it's moving along, maybe it's been pushed, and the only force is force of friction, notice that it's in the opposite way, yet the object could still move. Now, what does that actually mean for us in terms of work? So this is also a pretty neat idea, because now the actual two vectors, so meaning the force vector and the displacement vector, notice I put x in here, so those two are in opposite directions entirely. And this is another neat thing, that cos of 80 degrees, if you put it up in your calculator, if you still remember it from your trigonometry, okay, then this is actually -1. So that's what you would have. So if you were calculating the actual work in here, so work would have been, so notice 25 newtons, so this is my force, check, multiplied by 20 meters, this is in standard units, check, but then you're going to take cos of 180, and if you take cos of 180, this is going to be equal to -1. So what you're going to have is, you're going to have 25 multiplied by 20, and then multiplied by -1. So what this will be is, it's going to give us a negative actual, okay, this would be Newton meters, and we can certainly calculate this, 25 multiplied by 20, which is going to be 500, but it's -500 joules. So in this case, okay, we're actually taking the energy kind of out of this particular object, because if you would imagine, if it's friction, then that particular friction is going to be opposing, right? So it's going to slow this object all the way down. And that's going to go back, and once you start studying, how much energy you have when you're in motion, and then how much energy you have when you're not in motion, well, you're going to be losing your energy that you have in motion. That energy in motion typically is called kinetic energy that you have, okay, and you're going to be kind of losing, or it's going to be dissipating it out. So this negative, okay, is actually meaningful for us. So in general, that's what we have. So you can have basically both positive and negative energies, okay, my apologies, work, okay, forget the energy word, okay, for the moment. So you can have positive and negative work that is done on the object, okay, and that will depend on the angle in between. And here is your standard definition. So that's the definition that you will start utilizing, and I encourage you to get comfortable with the cos button on your calculator. All right, so that is it for this introduction. Hopefully we'll get into some word problems where you can see this in action. Thanks for watching. Bye, everybody.